Yeah, so I mean, if I have a basis UI of my topology, right, then any open set U can be written as a union of these guys. I don't lose any generality by just assuming it's the whole thing. And so, if I have F of U and G of U, right, then there's a map to the product of F of UI and U, right? And applying my known map on these guys gives me a map here, right? And the identity property of sheaves is exactly that this map is injective. Yes. Right, so this is part of the definition of being a sheaf, is that these maps are injective. So there's only one possible map from here to here. That's and furthermore, map also have that I'm sorry, I'm going to do this. Right. This part of the diagram is going to be weirder. Another question you might ask is, well, if I define these maps on elements of my basis, and I show that they're compatible with all the restriction maps between elements of my basis, then does that actually force there to exist a map from FU to GU? And the answer is yes. So the uniqueness followed from the identity property of sheaves, that I can figure out what a section of a sheaf is by knowing its restriction to an open cover, right? And then the existence uses the gluing property. So you can extend this picture in the sense that I can put here F of, no, I don't want to try to actually write this out. I would put the intersection of these guys, and then I would need to pick an open cover of the intersection, etc. But if I have an element of F here, I can look at its image here, I can map here, and the question is, well, there can only be one thing that has these restrictions. Is there a thing that has these restrictions? And the answer is yes, because I can check that by picking an open cover of the intersection by elements of my basis and then use them. I mean, right, what am I saying here? If I have some FIs here, right, and I can map those to GIs, and the question is just, do the GIs, are these compatible on overlaps, right? And I do know that because the intersection of applied to the intersect, right? Not going to limit. I think you can all. Yeah. Thinking about the basis, it's a little weirder. Like, right? What do I have to map into here? I have to map into the collection of all pairs I and J, K, uh, on the equalizer of that map. Well, the it's balls, right? And Rn, right? The intersection of two open balls isn't an open ball, but it has a cover by open balls. Okay. I mean, if you know, you can try another source. Uh, mhm. And the Zariski topology on spec, the intersection of two basic open sets is a basic open set. But you can have schemes where you have two affine open sets and their intersection isn't affine, right? So two and A2, and right, we talked about this construction where you can identify me an A2 with a doubled origin, right? And well, these two A2 there are sort of often cases where you can get these nice bases, but you have to be a little bit careful. So one important example that we were just remind you what we were talking about in the previous class. We had talked about starting with this more cluttered, but just to be sure that we match with the book, S dot just means the whole ring. And we defined this space, proj of S, homogeneous topology on this guy. One of is the oh, that is unfortunate. Okay, it's a good start. Yeah, it automatically records. So that luckily it's pretty easy, pretty hard to mess that up. Hmm, interesting. Oh, I don't know. I guess we just have to soldier on. I mean, I can try just like
all right. So this is describing this guy as a topological space. This is a basis of open sets.
and I was reminded that we should go down this road by Jack's comment that if I take two of these guys and intersect them, then that is again an open subset of the same thing. And we finally, just at the very end of class, so I want to kind of emphasize it again, talked about the scheme structure on this guy. So in order to tell you the scheme structure, what do I need to do? I need to tell you what the sections of the structure sheaf are on a basis of the open sets. And everything else will fill in exactly by this sort of argument of being able to write sections of a sheaf as a equalizer, blah, 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 but as gluing together sections of the basis. All right, so I define the structure sheaf of proj of S on one of these distinguished open sets to be, so I take the whole ring, I'm not going to write the dot just to make my life a little easier. I localize F here, my F has to be homogeneous. So this is all the things of the form R over Fn, R in S, and a non-negative integer. So this is again a graded ring, but now with the grading over Z, where the degree of this guy is the degree of R if R is homogeneous minus n times the degree of S. So this only makes sense as a graded ring if F is homogeneous. All right, but I'm not done yet. I'm going to take the degree 0 part of this. So the thing to sort of think about here, so we're ultimately going to want this sort of construction is exactly cooked up. So that proj of the polynomial ring is going to be isomorphic to Pn of k. And this is going to be a definition, but it should behave like this Pn. So in particular, if I take a homogeneous polynomial, so let's think about C x0 up through xn, if I take a homogeneous polynomial in here, well, that doesn't define a function on the set Pn of C. For now, let's just talk about the kind of usual points of Pn. They're lines in here. So x0 up through xn don't have values. They only have a value if I take the ratio of two polynomials with the same degree. So this exactly makes sense if the degree of G is equal to n times the degree of n. Or the degree of this guy is 0. So this is sort of a different problem of not being a function from the one we've talked about with affine schemes of like an integer isn't a function on the set of primes, right? Here, even in sort of the complex world, this G isn't a function, it's something else. And in order to get something that is a true function, I have to take the ratio of two things of the same degree, which is why I end up with degree 0 here. Okay. So, what do I want to say about this? This is a good point. So let's talk about examples. So as I say, I define, this is the definition of projective space in sort of scheme land, is that I take Raj of the polynomials with coefficients in K. And again, K doesn't have to be a field. K is any commutative ring. Right, and I define, this is my definition of Pn over the ring K. So what do the points of this look like? Well, if K is C, or more generally, an algebraically closed field, then I can get these relations by saying, okay, if right, in this case, I should think about, well, I have these actual coordinates, right? Right, a point in here is defined by setting these guys equal to this up to scalar multiplication. So what does this tell us? It wouldn't make sense to look at the element x0 and to say that's equal to a0. I know that that doesn't, x0 isn't a function. I can't assign it to have a value. And exactly the reason that doesn't work is x0 minus a0 isn't a homogeneous element of the polynomial ring. So I can't use that guy, but I can use ai xj minus aj xi. Right? This is homogeneous of degree 1. All right, and if one of a0 up through an are not 0, then this defines a maximal homogeneous idea. But I have to be careful here. Maximal amongst those not containing. the irrelevant ideals. So what actually happens here if I try modding out by this ideal? So in the usual polynomial ring, I would have set my variables equal to scalars, and I would just get a quotient, which is a copy of C. Well, here instead, if I mod out by these guys, what I end up doing is I mod out by a codimension 1 subspace of my degree 1 things. So these always span. Here I'm using that one of the AIs is not 0. And codimension 1 subspace. Degree 1 things. At least one. Sorry? I mean, if all AIs are 0, then these are all 0, and that's not interesting. Right, exactly. So, yes, right. So to get an ideal of the right type, I need a point in projective space. That's the point I'm trying to make, right? That you are naturally led to the condition that one of these guys is not 0 by the fact that you're looking for an ideal in here. Yeah. Oh, yes. Right, but depending on which of the AIs and AJs are 0, you can't say which ones are redundant and which ones aren't, right? So if I look at phi of x0 up through xn, mod the ideal generated by these AI xj minus aj xi's, right? Then what am I going to get? This is going to be isomorphic to polynomials in one variable, where this y is, well, the image of one of the xi's, but I can't tell you which one it is, right? Y is just any non-zero element of the quotient, any non-zero element of degree 1. Right, so if I'm on the open subset where x0 is not 0, then I could define y to be the image of x0. But then there's a closed subset where that doesn't work, and I have to take x1. Well, but there's still a closed subset where x0 and x1 are both 0, and then I would have to take x2, etc. Right? So one of the sort of extreme cases of this is if I take all of these coordinates to be 0 except for one of them, then the only one of these xi's with non-zero image is this guy. Set all the other ones to 0. But always one of the xi's has non-zero image, and I could take y to be that guy. So this is actually taking me to an important point. If I take Raj of, more generally, A of y, every homogeneous ideal in here that doesn't contain the irrelevant ideal has to be of the form, take an ideal in K and just add y to it. So this proj is actually isomorphic to spec of K. And this is saying that P0 is a point. This is P0. So P0 is the same as A0. All right. And so what I'm getting here is when I take the closed subset corresponding to these elements, then I get something isomorphic to spec to proj of the quotient, which is just a copy of spec C, so a single point. All right, on the other hand, just to do one more example where we see something a little bit interesting, what happens if I look at P1 over Z? So what do homogeneous prime ideals in here look like? Well, there's a bunch of them that just come from prime ideals in Z. So I still have this sort of picture of, for every prime, I have a line that I'm drawing. I keep thinking that 4 is prime, but it's definitely not. All right, and then I'm going to have lines going the other way, where I take, well, I could start with degree 1 elements of my homogeneous elements of this is, right, this is corresponding to Z of x0, x1, right? But more generally, what I'm going to look for is polynomials which are homogeneous, so homogeneous polynomials. In x0, x1 that are prime. And this is a UFD. So principal prime ideals are just ideals generated by elements that can't be factored. And if I think about what these are going to look like, because it's homogeneous and I have 2 variables, I just have the degree of homogeneity, and then I tell you how many powers of x0 I have, and it determines how many powers of x1 I have. So I have some, a n x0 to the n x, oh, there's no x1 then, a n minus 1, x0 to the n minus 1, 1. So really, all my information is in a polynomial in one variable, right? I could just look at the polynomial where these a's are the coefficients and write this as x1 to the n times f of x0 divided by x1. And asking for my homogeneous polynomial to be prime is just asking that this guy be prime. Okay, so what kind of points am I getting here? I'm getting prime ideals, irreducible polynomials with integer coefficients. So the sort of things going the other way correspond to algebraic integers. This corresponds to an algebraic integer up to the Galois action. Right? I'm only getting the corresponding minimal polynomial over Q. So I get one prime ideal for each Galois orbit of algebraic integers. All right. On the other hand, I also have these intersection points. So I get over here, I'll get points corresponding to P1 over FP bar, again, up to the Galois action for FP bar over FP, corresponding to I take 2, I take my minimal polynomial of one of the coefficients of the point here, I get this. And maybe the thing I'll note here, right, it was a little arbitrary whether I did this or I did x0 to the n f of x1, x0. So I have to also remember that I have points that correspond to both 1, 0 and 0, 1. Yeah. Oh, triggers. Okay, great. So again, these projects, they sort of contain a lot of information, right? All the different projective lines over all the different primes are all hiding in this P1 of Z. Yeah. Mhm. Yes. So in general, right here, so in this proj, well, whenever I choose a homogeneous polynomial, I get an affine open set. So inside here, I have a ui that I define to be d plus of xi. And you can check that this is going to be, right, what happens when I localize xi and take the degree 0 elements, right? I get exactly, so this is going to be spec of k of x0 divided by xi, dot, 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 up through xn divided by xi. So I needed degree 0 elements. So I exactly get these quotients. I've inverted xi. So you can see that these guys glue together when you sort of consider the overlaps by exactly the formulas I wrote last time. So in theory, sort of all the other open subsets that come from inverting other homogeneous polynomials are kind of redundant, but it's kind of more canonical to just consider all of them and think, well, I can glue all of these guys together. Sort of convenient to not have to choose these, what your coordinates are. All right. Do, 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 do. Any questions? All right, so we'll talk more about these guys later. Let me just put down definitions. We call a scheme X projective over K, or because it's annoying to keep saying over K, or a projective K scheme. X is proj of S dot, or S dot a finitely generated rated algebra. Yeah. Mhm. Uh, oh, like which one corresponds to which one? Yeah, sorry, I didn't think carefully about that. Right. The point 1, comma 0 corresponds to the ideal set x1 to 0, right? This corresponds to the homogeneous ideal generated by x1, right? To specify this point, I just have to tell you that x1 is 0. And 0, 1 corresponds to the homogeneous ideal generated by x0. So more generally, right, if I have any point in the projective space of over Q, well, I can pick coordinates for it that are integer, right? And I can look at the ideal generated by bx0 minus ax1. that's a prime ideal, and it corresponds to this point in P1 of Q. Right, and I'm just thinking about, yeah, I can sort of define, because I can think of these elements of this ring as functions on P1 of Q, functions in the sense of, up to the weird scaling thing, or as on P1 of FP or P1 on any field extension of FP. I can take points in all of those spaces and say, look at the ideal of homogeneous polynomials that vanish at this point, right? So like this ideal corresponds to the generic point of P1 of FP. And then on here, there are individual points that correspond to the points in the usual sense of P1 of FP. Yes. Yeah. But I mean, somehow what you get from what you sort of see when you write things down is that you get points over all finite field extensions of FP, right? Because I can take, just as here, I can take a point in P1 of this guy. So I have some A and B in this field extension. And it still makes sense to take a polynomial in the integers and evaluate it on A and B. Think about that as an element of FP bar and look at which ones are zero. Right? This is kind of the nice unified way to say that. And obviously anything that's divisible by P is going to be zero, so it contains this ideal. But now I'm also going to get sort of a more sort of degree, not necessarily one, but things coming from kind of the minimal polynomials of these elements. So similarly, from this sort of story about algebraic integers, I could do exactly the same story, but with points in any finite field extension of Q. And I would similarly get an ideal where I could think about doing this evaluation, but thinking of it as an element of Q bar and seeing which things I got that were zero. All right, so this is a very strange space, but it sort of got all these things we're interested in hiding inside it. Oh, sorry, sorry, Caleb. The projective K-scheme. We also will sometimes use the term quasi-projective to mean an open subset of a projective. So this just sometimes comes up that you want to consider open subsets of projectives that maybe aren't affine or aren't even an open subset of an affine. Yes, when I say graded, I mean by z greater than or equal to 0. But look, I'm matching the notation from Vakil. You can take up with him whether that was a good choice of notation or not. All right, so this is sort of a nice supply of schemes which aren't just affine schemes, and they allow us to kind of combine thinking about non-algebraically closed fields, characteristic P things, etc., and projective stuff. All right, I've only got a little bit of time, but let me start talking about properties of schemes. So you could spend a lot of, it's going to be one of the push and pulls of this class, how much time we spend talking about all the different properties that schemes might or might not have. We had this conversation at the start of class last time about like, oh, maybe the thing I called schemes should be called pre-schemes, and schemes should be something with some more hypotheses, um, which is fine. But then you have to agree on what the hypotheses you want are. So one you extremely often want is that a scheme is Noetherian. So we call a scheme Noetherian, well, if the underlying topological space is. All right. That's pretty self-explanatory. We've already covered the definition of a Noetherian topological space. As I said, for an affine scheme, this doesn't guarantee that the ring is Noetherian, but it gives us sort of enough nice properties that it's good enough for most things. This one is sort of more debatable whether you really need to worry about it, but it is sort of important for getting some, more easily checking some other properties. So we call a scheme quasi-separated if the intersection of quasi-compact opens are quasi-compact. So the point somehow here is, because I took the most generous imaginable definition of scheme, you can cook up some really weird stuff if you aren't careful. So this is a property you should expect to hold for all reasonable schemes. And maybe I should have just made it part of the definition of scheme. In order to get a counterexample to this, you need to do something like look at spec of infinitely many variables and glue that with itself, removing the origin. So double the origin in here. So a kind of standard example of a scheme which is not quasi-compact is take this guy and remove the origin. So in a finite dimensional affine space, you can remove the origin and you can cover what's left by finitely many affine open sets, which come from inverting the coordinates. Well, now that's not a finite cover, and you really need the guy where you invert all the coordinates, because I didn't tell you which coordinate wasn't zero. It could be any one of them. So if I double the origin in this guy, I have my two copies of spec. Spec of anything is quasi-compact, even something really horrible, but their intersection is this guy minus the origin. It's not quasi-compact. So this is mostly just a lesson of if you say, oh, scheme is anything that's locally isomorphic to an affine scheme, there is some really horrible stuff in there, and you need some extra hypotheses to avoid doing this dumb stuff. All right. Now some real important properties that actually sometimes we'll want and sometimes we won't. I mean, it'll be incredibly uncommon that we would want to consider a scheme that isn't Noetherian. So X is reduced. So reduced, you should think of this as the algebraic geometry word that corresponds to a ring being radical. If for all points in X, the local ring XP is radical. So as in has trivial nilpotent radical. That is, if I have a nilpotent element, then that element is zero. All right. So if X has an open cover, by UI, which is affine, then you can actually test being radical really easily. Um, X is radical, X is reduced if and only if each of these rings is radical. So this is just, if I have a ring that isn't radical, then one of its local rings isn't radical. And on the other hand, if these guys are radical, well, every local ring is a localization of one of these rings. So it's radical. All right. So somehow, this local ring, I know we haven't talked about it a lot, but it's always that you have a point in your scheme, and from the perspective of that point, it looks like you're in an affine scheme, right? You have sort of a chart. And so this local ring is always computed in there. So for example, right, if we went here to this P1 of Z, we have all these kind of weird points, but every one of them sits inside one of the affine opens where I either set x1 to be not zero or x0 to not be zero, right? Modulo any prime ideal, one of these guys has non-zero image. Because if they both had zero image that was zero, you would contain the irrelevant ideal. And so the local ring of any point in here, I can compute by just passing to one of these affine opens and computing a localization of that ring. So it's going to be a localization of ZX1, of this polynomial ring, either this quotient or the quotient the other way around. Right? The open subsets where x0 and x1 are not zero are spec of this polynomial ring and spec of the inverse guy. All right, cool. Sorry? Yes, because any power of something zero being zero implies that thing is zero. I mean, the spec of the zero ring is nothing, right? It's the empty set. So I am comfortable saying that the empty set is reduced, right? Because this is a condition about every point in the scheme. So it's trivially satisfied by the empty set. All right, so this is a property which, often we will want to ask for, but it's very important that non-reduced schemes exist, right? We sort of at least talked a little bit about this story, for example, with Bezout's theorem, where you can take two prime ideals in, well, irreducible closed subsets inside P2. And when you intercept them, you want to remember that their intersection points might be schemes which aren't reduced. That's exactly how you remember the multiplicity of the intersection. All right. A similar thing we'll often want is X is integral if, just make sure I get this right, OX of U is a domain for all open sets U. So I could have defined this property by saying that X is reduced if and only if the sections on every open set are radical. But it's sort of nicer to say, no, it's a local thing. It's something I have to check at each point separately. So it's sort of important. This is not a stock local property. It's not a property you can check by just checking something about each stock. So if X is integral, then these local rings are domains, but not enough to check. And the reason, which was covered pretty extensively on question 1 and homework 2, is that if I take a disjoint union, I will always get something which isn't a domain. Right? I'll get the direct product of 2 rings, and that's never a domain. So I need to have the stock property, but I also need to not have any open sets which are disconnected. And unfortunately, it's 11:20. So I need to stop, and we'll talk more about integral guys next time. So this is sort of the scheme version of being a radical ring. This is the scheme version of being a domain. Maybe I'll just say one important thing here, spec R is integral if and only if R is a domain. And that's like not completely obvious. We'll have to talk a little bit about that next time. Right, it's obvious that R has to be a domain because R is the sections on the whole open set. But why is it that if I take any open set, I get a domain? Right.